few questions from our homework out of 4-2, and we're going to look at question 9, 14, and 15. Okay, so question 9. If you've got any questions out of the homework, just be sure and let me know, and I can put them on the projector here. But we're going to start with question number 9. Now, we did some similar questions in class last time. Very similar. We're going to, remember, have to use the E function in our calculator. So that's a special function. Now, on this one, this is radioactive decay. Exponentials and exponential modeling is used for things where we have either an increase over time dramatically or decrease. If it's negative like this one, it's a decrease because radioactivity decreases over time at an exponential rate. It's positive for things like bacteria growth, population models. They're also an exponential. Now, E is just like pi. It's just a number, and it's built into your calculator. So for question 9, we want to use this model where T is the time in years. The initial amount is 243 milligrams present. Find the amount left after 72 years. So we want to determine how much radioactive material is left after 72 years. So we use our formula, which is A of T equals 243 E to the minus 0.014 T. And we want 72 years. So that means my T is going to be 72. Okay, so T is going to be 72, and we'll plug that value in. So we're going to find A of 72. And that is 243 E to the minus 0.014 times 72. Is everyone all right with that so far? Now, what do? Well, we need to use our calculator. And so this is nothing but a calculator problem. And so the first thing I'm going to do is I'm going to work in my exponential. So we'll do that first, and we'll multiply those together. So I've got 72 times 0.014, and it's negative. So that gives me now a 243 E to the minus 1.008 power. Is everyone okay with how I did that? Next, we need to make sure that we know how to use our calculator. And again, there's two different types of calculators. I'm going to show you how to use either one. You might have a calculator like this one. So for a calculator like this one, how would you use this calculator? Well, first thing you would do is you would type in your 1.008. You'll make it negative. Let me make it a little bit brighter here. There we go. Okay, so we'll make that a little bit brighter. Make sure it's still plugged in. Yep. Okay, so that's going to be our number in our calculator. Now, either type of calculator, somewhere you're going to have an ln key. So you're going to have to type inverse ln. That's going to make the exponential. And then once you've done that, then you multiply that by 243, and that gives me now to the nearest milligram 89 milligrams. And that's going to be your answer. Another type of calculator that many of you might have is this calculator. Or something like this. This one has a screen. It's done a little bit differently. Either type of calculator, though, you have the ln, and ln is the natural log. And see how it says e to the x here? See how it's in blue? You'll type second first, ln. That's going to put the e up on the screen. And then you type your number in. Now, very important, use the negative here, not that one. So use this key right here with the parentheses around it. And then we'll type in our number, 1.008. And then we hit our enter key. And then we multiply that by 243. And so either way we do it, we then round to the nearest milligram, and we will end up with 89 milligrams. So we use our calculator to evaluate it down. Now, 14 and 15 are almost the same. We're using our exponential key in our calculator. And E is just a number. It's built in. Question 14. On question 14, we've got a formula. So an element decays at a rate of S of t equals S e to the minus 0.50 t, where S is the initial amount in grams and t is the number of years. If you have a 13-gram piece of this element, how many grams will you have 3 years from now? And we want to round to the nearest tenth of a degree. Why is it negative here up top? It is negative here because what's happening to the radioactivity? Okay? If you think about Chernobyl or any of the other nuclear events, what happens? Over time, the radioactivity decreases, right? It's not quite safe yet, but it's getting safer all the time because this negative is saying it's decaying. If it was positive, like population, it would be a positive value, and population would be going up. This one's actually going down. Here's our formula, and we need to put the pieces in. So here's our formula. So S of t equals S e to the minus 0.050 t. And we're going to have to use our values. Now, S is the initial sample size, which in this case is 13. And our time, t, is 3 years. So we're going to use a time of 3. So that's what we have there. Okay, so that's our formula. We're going to plug our values in. So we want to find S of 3 equals 13e to the minus 0.05 times 3. And we'll go ahead and break this down a little bit here. We're going to multiply, so that's a minus 0.15 if we round. Is everyone all right with that so far? So what did we do first? We did our exponential here. How do we now plug this value into our calculator? Depending upon which type of calculator that you have, we'll do this one first. You type in the 1.5, you make it negative. Second, ln, or inverse ln. And then what do? Multiply that by what? 13. And we want to round this now to the nearest tenth of a gram. So that would come out to be 11.2 grams. So after 3 years, you only have 11.2 grams of that radioactive isotope left. How would you do it in this style of calculator? Most of you have one style or the other. This one, we approach it the same way. A little bit different though, because we do second ln first. That puts the e there. Then we do, and again, which minus do we use? We use this one here, parentheses, not this one. Don't use that one. In blue, use this one. So use that key there. And then what's our number? 0.15. We hit our equals, and we multiply that then by what? 11.2. And that, or not 11.2, sorry about that. We want to multiply it by 13. Now I'll clear it out again. Okay, so let's, sorry about that. Let me do it correctly. I just typed in the wrong number. So we'll type in second, ln. We need a minus 0.15, hit equals. And then we're going to multiply that by what? 13. And that's going to give us the same 11.2 if we round it. Question 15 is another exponential. Try to get as much left on here as we can. So this one on 15, we are looking at mouse population at the local dump. So what's going to happen is we're going to have more mice, right? This is an example, again, of an exponential. Look at your exponential formula here. This is positive for your exponential. Why? Because the mouse population is going up. Unlike the last one, on the last one, this was going down because the radioactivity decreases. This one increases. So we're looking at increasing this mouse population. So the growth of the mouse population at a certain dump can be modeled by this exponential function, where t is the number of months since the population was first recorded. We want to estimate the population after 28 months. So we write up our formula. A of t equals 395 e to the 0.013t. And we want, in this case, 28 months. So that would mean then my t is going to be what? My t is 28. So I plug that in. And we multiply. So now we've got 395e, and we'll multiply here. We've got a 0.013 times that 28. That gives you 0.364. And now we can finish it. Again, we use our calculator, depending upon which type of calculator you have. I'll do this one first. So on this style of calculator, you would type 0.364. We need a second ln, and then multiply that by 395. And we want this, how far does it say to round? It says, estimate the population after 28 months. So we'll just round to the nearest whole number here. So when I round, it looks like it's going to be 568 mice. So you should have 568 mice after 28 months. We started with 395 because that's the initial number of mice. That 395 now grew to be 568. So it increased pretty quickly because 28 months is not a long time. So that mice population went up fast. How would I use this style of calculator? This one, a little bit different. We do it in the opposite order. Second, ln, 0.365, hit the equals key. Multiply that now by 395, and we round to the nearest mouse. And this one looks like it's going to be 369, right? Depending upon how you round. Just depend upon how many mice you have. One calculator is a little more accurate than the other, but 368, 369. But that's what you'd be expecting. Or, sorry, 568, 569. So either way, they're only one off, and that's just because of rounding. Did we have any other questions out of 4.2 to look at? Oh, thank you. Anything else out of 4.2 to look at? Any other questions? Anything else? Okay. Well, then we will go ahead now and look at logarithms. Now, logarithms and exponentials are inverses of each other. This is called a logarithm. y equals log base a of x. And so this subscript down here, this is your base. Now, logarithms are used when a small change is a large change. So some classic places where a logarithm is being used is things like pH in a physics course. Right? If you look at pH of water or pH of anything else, a small change is a big change. So when you go from like a 7 to a 10 on the pH scale, that's a huge difference. Same thing with earthquakes and tornadoes. Earthquakes are measured on the Richter scale. When you go from a 4 to 5 on the Richter scale, that's like 100 times more. It's a huge, more powerful earthquake. So Richter scale, pH, those are all examples of logarithms. Small change is a big change. You'll see logarithms a lot and exponentials in your physics course or your physical science course. That's where we use a lot of logarithms. Also use in statistics. If you take our elementary statistics course, you're going to see logarithms and exponentials, especially exponentials, being used a lot. When we go to graph these, we have to look at the base just like we did with the exponentials. So this is our exponential function graphs. This is going to be our logarithm graphs. Now, why is there two different ones? Because we've got two different ones based upon the value of a, based upon the base. If your base is bigger than 1, your graph looks like this. If your base is less than 1, your graph looks like that. So if it's a fractional base, it looks like this one. Whole number bases bigger than 1 look like this. So I'm going to give you a couple of these, and we're going to be graphing these logarithms. We'll start with a very, very basic one. So we're going to be trying to graph log base 4 of x. And that's going to be your a. Now, what do we know first? Just like we did with exponentials, we have to look at our base. Is 4 bigger than 1? Yes. So when we draw our picture, which one is it going to look like? Okay, 4 is bigger than 1, so it looks like that one, doesn't it? See how it's curved? That one goes up. This one is fractions and it goes down. So my picture is going to look like this. And notice it has 1, 0 instead of 0, 1, because these are inverses. So my picture is going to look like this. It's not shown, but just like with exponentials, there is a horizontal asymptote, right? In logarithms, we have a vertical one. So when we go to graph this, it should resemble this in a way. Am I moving this graph up or down any? No. Nothing's added on the end. So where is my new vertical going to be? We're not changing it. So my vertical is right there. Okay? And that is an x line instead of a y line. So there is my vertical at x equals 0. Now, normally, we would use 0, 1. But we're flipping it around, and we have to use 1, 0 for our starting point. Because what we need here is we always need 1, 0. And then we also need a 1. Okay, so that's what we have to use. We have to use a little bit different points here. Okay, so we've got our 1, 0 here. And what's my a? 4. So that means we've got to go 4 units over. 1, 2, 3, 4. And 1 unit up. And that's going to be at 4, 1. And what does the graph need to look like? That. So we've got our 2 points. You can use 3 if you want to, but you really don't need to. And when I curve it, the graph resembles that. That's how I did that. We're going to do several more. Okay, why did I start at 1, 0 here? Remember last class period when we looked at the exponentials. And the exponentials, they started at 0, 1, right? All the time. Remember that from last time? These start at 1, 0. Why? Because these are inverses of each other. So the x and the y get flipped. So for the exponential, we use 0, 1. For the logarithms, we use 1, 0. Because x becomes y and y becomes x. Because these are inverses of each other. If I draw them, they're going to be flipped over from each other. So they would be reflectable around that line y equals x. They are inverses. So we have to do it the opposite. That is why, instead of going up 4 and over 1, right, we go over 4 and up 1. So they flip around. So let's do another one. And this one's going to have a translation in it. Okay. So again, my base is the 6. So a basic picture would look like this again, just like the last one. Right? It's going to look similar to that. It should be curved more down, but it's okay. It resembles this. Remember, I always like to do a quick sketch over to the side. This is just a quick sketch, so I know it looks like that in a way. Now, what about that minus 4? Well, that minus 4 is where? Inside the operation, and it is a negative. Now, it does the opposite of what you think it should do. It's inside, so that's going to force it forward 4 units. Right? Nothing new there. So when I draw my graph, where am I going to start at? Where's my horizontal line? At 4, right? Or sorry, my vertical line. My vertical line here is at 4. So we draw that. And remember, from 3, 5, remember, these are called asymptotes. So that's going to be at x equals 4, and that's your vertical asymptote. Now, I do need my 2 points. So 1 point is going to be a unit in front. So it's going to be at 5, 0. So there's my first point, because we had to go over 1, right? Just like all the others. Instead of going up, we go over 1. And then what's my next point? 6 units from here. So 1, 2, 3, 4, 5, 6 units. Go up 1, and that makes my new point. How many units is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to be at 10, 1. I can now connect these together. There is my graph. Is everyone all right with how I did that? So you just look at the basic shape, slide it left to right, and then make your graph accordingly. Let's look at one that has a fractional power. When we do the fractional powers, they're going to behave, or fractional base, they're going to behave the same way. It's just that instead of going up, it's going to go down. Okay, so when I look at this one, my base is a half. So 1/2 is not greater than 1. 1/2 is less than 1. So what does the basic shape look like? Instead of going up, it's going what? Down. So the basic shape looks like this one here. So that's what the basic shape is going to look like. And I'll put a -2 inside. Let's do a -2 here, just so we have a translation. So that's just put the minus 2 inside there. That way we have some type of translation. This is a minus 2, so that means we're going to do what? We're going to force it now 2 units forward, so 2 units to the right. So my vertical asymptote, these have vertical, the exponentials have horizontal. So my vertical is going to be x equals 2. Is everyone okay with that? Now we need our 2 points. So our first point is going to be right here, and that's 1 unit in front. So that's at 3, 1. Now what is my base? Oh, sorry, 3, 0, whatever, 3, 1. Sorry about that. So it should be 3, 0 there. My mistake. Now, what is my base? Half. So here's my 2. I'm going to go forward a half and up 1. So that new point would be right here. And that's going to be at, this is 2. We're going to add a half. So that's going to be 2.5, 1. Because we had to add that half there. And now when we connect them together, it should make the picture looking like that. Okay, we connect them together, and you can see that it curves this way. Why is it going down? Because your base is what? Less than 1, so we have to use that half. So we go a half from that 2, so we're going to go half forward, so that makes it 2.5 and up 1. And that makes then my graph look like that, because that's back behind that 3. Is everyone okay with that so far? Now, when we work with these logarithms, many times it's going to be easier if we transform them into an exponential. And there's actually a formula for transforming these to an exponential. I'm going to give you the page number. And the page number for that formula is page 463, and I'm going to write it up as well. So page 463. If you don't have your textbook, that's fine. I'm going to write up the formula. And this is how we convert logarithms to exponentials or vice versa. So y equals log base a of x. That then transforms, and it goes back and forth either way, into x equals ay. So we're going to convert these. So we're going to convert them to either an exponential or we're going to convert them to a logarithm. Okay, so this is our logarithm here. How would I convert this into an exponential? The first thing we look at is we look at our pieces, and we need to label them. So here's our formulas. Here's how they convert. This 4, that is your y. The 2 is your a, and the 16, well, that's your x. When I convert it, what does that look like now when I convert it? When I convert this into an exponential, that 16 goes out in front. Then we have a, which is what? 2. And our y is what? 4. And does that make sense? Yes, because 2 to the 4th power is what? 16. Do you see how I converted it? Let's convert another one. Oh, well, let me write one up here. How about we do 2 equals log base 5 of 25. How would this one convert? Convert this into an exponential. Okay, first thing we do is we go to our formula, we label our pieces. So 2 is the y, 5 is the a, 25 is the what? X. So when I convert that, what does that now convert into? 25, you're correct, equals now 5 what? Squared. And that makes sense because 5 squared is what? 25. Now let's do the opposite. Let's convert this into a logarithm. So I'm going to give you a different one. We're going to convert this one from an exponential into a logarithm. Okay, this is an exponential. I want to convert this into a logarithm. So what's our formula? Our formula is y equals log base a of x converts into x equals a y. So this is an exponential. So that a, well, that would be your a. The 2, well, that would be your y. And the 64, well, that is your what? X. So what would this look like if I were to convert it? 2 equals log base, 8 of 64. Yep. So do you see how I converted them? If you need to, write up your formula every time and label the pieces and then convert them. Now what we're going to look at next is we're going to learn how to use our calculator to evaluate down logarithms. So we're going to use the calculator here. And it's going to be log base 10. Log base 10 is the same as just log. In many cases, we don't put the 10 there because 10 is the common base. Okay, so log base 10 is the same as just the base log. It's like the square root. We don't put the 2 in front of the square root. We understand it's a square root, not a cube root. Same thing with the logarithms. Whenever it's log base 10, we can use our calculator. So if you look at your calculator, right next to the ln key, you're going to see the log key. So how would I evaluate down log base 10 of 9? I would then type in, on this particular style of calculator, log, that puts the log on the screen, 9, and hit equals. And what does that come out to give you? We'll just take it out to 3 places. That is 0.95 if we round 4. Let's try another one. What would log of 12 be? I'll use the other calculator to show you. It's going to give you, work out the same way, a little bit different though. In this style of calculator, if you have this old style, how does it work? Well, in this one, you've got to type your number in first, and then the logarithm key. And that gives you 1.07 if we round 9. Is everyone okay with how we use the log key in a calculator? Now, that log key is for log base 10. So these are the same. If there's no number here, it's log base 10, and we can use our calculator. We cannot do log base 4 in our calculator. Next week, we'll learn how to use the change of base to evaluate things down with different bases. But right now, the only ones that we can work on are log base 10. Now let's try another one. Now, how would we work this one out? Yep, and I'm going to show you 2 different ways of working this one out to get the same result. One way would be, I would go ahead and take that 4 to the 5th power. So 4 to the 5th power is going to be 1024. And now I can use my log key, and that gives you now 3 point, if we round, 010. So that's one way of doing it. Now, what's another way? Well, we also have some special rules that we can use for logarithms, and sometimes these rules are very helpful. The only one we use a lot is your power rule. And the power rule says this. So the power rule says this. If I have a power, I can bring it down. So I'm going to show you, if I work this one out with the power rule, I would get the same result. So if I want to do log base 10 of 4 to the 5th, well, what I could do is I could bring this 5 down. And in some cases, this is helpful, because it does make problems easier. And now we got 5 log base 10 of 4. And what does that come out to give you? Let's see if it gives you the same result. Okay. Log base 10 of 4 is that. Multiply that by 5, and see it gives you the same 3.010. It's the same, right? Now, why is that helpful? Well, in some cases, like the next one, you're going to have a decimal. And it's much easier to just bring the power down than to deal with it any other way. And again, we're going to use our calculator. And how about we look at this one? How about log base 10 of 0.0073 to the 8th power? I wouldn't want to do this in my calculator, because look what's going to happen. If I try to do this in my calculator, 0.0078, I would take that then to the 8th, or 7.3. We'll take that then to the 8th power, and see, it's going to put it in scientific notation. It's going to be hard to deal with. What's the easier way to approach this one? Okay, the easier way to approach this one is just simply take this 8 and do what? Move it down. That's our power rule for logarithms. And that's about the only one that we use on a regular basis. There's others, but that's the most common one that we use. Now, we don't even have to write the 10, because we can just write it as log. Remember, base 10 and just the log are the same. So if you don't have a number, it's log base 10. What would this now come out to be in our calculator? Well, let's try it. We need the log of 0.0073. And then we'll multiply that by 8. And that comes out to be a minus 17.093. Let's do one more like this, and then I'll give you a different one, where the log is up top as a power. So let's do one more. We'll use the calculator like this. How would I evaluate this one down? Well, the first thing I would do is, this is a power. Powers can come down. Makes it easier this way. So I'm going to bring that down as a power. So then I have 9 log of 0.473. And we need the log key first, 0.473. Multiply that by 9. And then it comes out to be a minus 2.926, if you want. Is everyone okay with how I do that? Bring the powers down first. It's going to make it easier. I mean, you can do it either way, but I think it's much, much easier if you just simply bring the power down first. Now, what if your logarithm is up the top? What if your logarithm is a power? What if I gave you this to break down? And I'm going to try to pick one like your homework. It'll be a little bit different, but I'll try to pick one that's similar. What about if I gave you this one? Okay, how would I break this one down? Well, there are ways of converting it, which we can convert this into an exponential. I think, though, the easier way is to just use our calculator. So what I would do first is I would do that. That's my exponential. I would do that first. And I'm going to show you how to use the automatic memory in your calculator. So, log of 9 is that. Now, what do I still need to do with this? Not multiply, this is raised to the what? 8th power. Now, if you notice on your calculator, a lot of calculators have this A and S button. That is your answer. It's a stored memory. So, if I want to keep this, I can then just type 8 caret the answer key. So second, the negative symbol. And that stores it. And that is going to give me this. Which is 7.27 if we round 4. Now, what's another way of doing this? If you don't want to use the memory in your calculator, you can do this. What's log of 9? If you have trouble using your calculator with the memory, what's log of 9? Log of 9 is that. Now, take it out to at least 5 places. That way you don't lose anything for round off. And now you could just use your calculator. So either way, it's going to give you the same result. Right? If you don't want to use the memory in your calculator, you don't have to. You can just write it down and just plug the number in. And it gives you the same, right? 7.274. So you can either use the memory in your calculator, or you can just write the number down. Now, if you go on and you take a statistics course, you're going to be using the memory in your calculator a lot. In this class, we don't use it very much, but in statistics, you'll use a lot of logarithms and a lot of exponentials and a lot of calculator work. So in statistics, you use the calculator a lot more. For the next ones, I am going to give you a function, and you're going to have to find the base and then evaluate it down with a new value for x. So here's one, and there's a couple of these in your homework. I'm going to work out 2 of them, and then I'll do 10 in your homework and leave 9 for you to do. And let's see, how about f of 9 equals 2. Okay, and I want you to then find f of, how about f of, let's plug a number in here. How about f of, number with a good square. How about f of 49? That'll be a good square. Okay, so make sure I've got this all written up right here. Yep, and that's going to be 49 there. And you want to find that f of that value. So the first thing I've got is I'm going to use this one first. So we know that f of 9, what would f of 9 look like if I use my formula? Well, f of 9 would be log base a of 9, right? Okay, now, what would this look like? F of 9 is what? F of 9 is 2. And let's not do 49. Let me come up with a good cube. Let's make this 27. That way it'll come out to a good cube. I have to make these up because they're not in your textbook. But let's use 27 instead of 49. Sorry about that. 27 is a good cube. Now, how do I find the a? I need to find the a. I find the a by rewriting it. Remember, how we rewrite this is y equals log base a of x, and that transforms it into x equals ay. So we're going to transform this into a logarithm, find the a, and then we'll do f of 27. So this is your y, this is your a, and this is your x. So by transforming it, okay, if you transform it, what would it look like? There we go. I was hoping that somebody didn't lock the door on us, but okay. So we want to go ahead now and transform this. If I transform this into a logarithm, into an exponential, what does it look like? If I transform this, this looks like x, which is 9, equals a to the second power. Now, we learned how to solve this last time, or you can use the square root property. Either way, how would you figure out what this would be? Well, we know that, and there's two ways of doing it. You either take the square root or know that 3 squared is what? 9. So you could convert this into 3 squared equals a squared. And if the exponents are the same, right, then the bases must be the same. So a must equal what? 3. You could have also gotten that by using what? Square root. Because what's the square root of 9? 3. You can either look at it like this, because 3 squared is 9, and rewrite it, or you can just simply use a square root property. What does our formula now become? Our formula now is this. F of x equals log base 3 of x. And I want you to now find, this is what I want you to do, find f of that 27. So we had to find our base first. Once we have the base, then I want you to find f of 27. So what would f of 27 look like? The f of 27 would be log base 3 of 27. We've done these before. I cannot use my calculator. Why can I not use the log key in my calculator? Because this is log base what? 3. Our calculator can only do log base 10. What we then have to do is convert it. So this is going to be like our y here. So y equals log base 3 of 27. This is your y. This is your a, and that's your x. So what would that convert into? That would convert into now what? If we rewrite it, it's going to convert into 27 equals 3 to the y power, right? And what do we know about 27? Yep, we need to make sure they have the same base. So 3 cubed is what? 27. So 3 cubed equals 3 to the y power. Then that means y must equal what? 3. And so that is f of 27. So f of 27 then is going to be 3. Let's do another. we'll do one more of these, and then I'm going to do question 10 from your homework, because that one is a little bit tricky with a square root base. So let's do one more with the whole number base. Okay, so let's suppose, and I'll have to make one up, that f of x equals log base a of x, and f of 343 equals 3. Okay, so let me make sure I got this right here. I'm going to have you find now a different value. So I'm going to have you plug something in here. And let's find f of, let's do 49 in this one. Okay, so what do we know? We know that we have this. So we want to find f of that 343, and that's going to be log base a of 343. So that means this is 3. Now, how would I now convert this? What would this convert into? This is going to be now converted into the y for the 3. A, and that's x. So when I convert that, I have 343 equals a to the third power, right? How would you solve this? You can either use the cube root, or you can think about that 343. And 7 cubed is what? 343, isn't it? Right? Because we need that exponent of a 3. So that would be 7 cubed equals a to the third. So that means now that a must equal what? 7. If the bases are the same, then the exponents must be the same. Exponents are the same, the bases are the same. So you have to either get the exponents to be the same number or the bases to get the other one. So now what does our function look like? So now when we rewrite, we've got f of x now equals log base 7 of x. Now I want you to use that last part. So now I want you to find f of 49. So f of 49 would be log base 7 of x. 49. So it's going to go there. I'm going to call this y because that's what we're going to be finding. We've got a base of 7. That's your a. And this part is your x. So when I convert it, this is your y here. When I convert it, I now get 49 equals 7 to the y power. And what do we know about 49? 7 squared. So 7 squared equals 7 to the y power. And we know that the bases are the same. So therefore the exponents must be the same. So y must now equal what? 2. Next, I'm going to work out question 10. Question 10 is a more difficult question. Yeah, that's what that means. F of 49 is 2. Sorry about that. And that's your answer there, because that's what you're trying to find. Right? Because 7 squared is what? 49. And you can look at the base and see. It's a power of 7. Right? So 7 to what power gives you 49? 7 squared. That's how that base works. I'm going to work out 10 from your homework. And 10 is a trickier one, because 10 is going to have a square root for the base. Okay, so let's work with this one. Same procedure. So f of 5 is going to be log base A of 5, and that's a 2. This is your y, that's your a, and 5 is your x. So now when I rewrite this, this gives you 5 equals a squared. Now, logarithms can never, ever have a negative base. So when we take the square root, we don't have to worry about the plus or minus because you can't have a negative logarithm base. So all we have to worry about is the plus part. So I'm going to get get rid of the square by taking the square root. So that tells me then that a is going to be what? Square root of 5. That is our base. So now we can rewrite it, and we can find f of 125. So rewriting, we've got f of x equals log the square root of square root of 5x. That's our formula. And this one's a little bit trickier because you have a square root base. We want to find f of 125. And that would be log base square root of 5 of 125. Let me move this up so we can keep track of what we're looking at here. Sorry about that. So this is what we've got. How do we convert this? This is your y. That is your a. And that's your x. Okay, so when we convert that, yep, we got it. 125 equals the square root of 5, right, to the y power. Okay, how do we work this one out? Well, what is our end result? Our end result is we have to get this into a common base. Now we have two ways of working with this. We can either convert that 125 to a square root of 5 base, or we can work with the square root of 5. I think the easiest way is whatever you do to one side, you've got to do to the other. So how can I get rid of that square root? Square it. So that's what I'm going to do first. So I'm going to square both sides. So that's going to be done first. So that square and that square root go away. So this side comes out to be y to the 5th power. Or 5 to the y power, sorry about that. And that's going to equal 125 squared. And 125 squared with our calculator is this. Uh, 1565. 625. So 15625. 5 to the y power. Now, what do we know about that 15,625? Well, what does it need to be in common with? Sure. You could have done it as a fractional power as well.
So here it's like 5 cube is 125, right?
Right.
So when we square both, then like this cube.
Yes, and you'll eventually get the same result. Yep. I'm going to get the same result because you could have brought it to a fractional power as well. Okay, you're going to get that same. We're going to get y equals 6 eventually. Either way you want to look at it, you can either use different techniques. Whatever technique you use, you're going to get y equals 6. So what do we know now here? What do we want for the common base? All right, we want the common base of 5. So 5 raised to what power is going to give you this 15,625. We just use a calculator and check it. We know it has to be 5 raised to some power. So 5 squared is definitely not going to work, right? Because that's 25. 5 cubed is 125. 5 to the 4th is 625. 5 to the 5th, we're getting closer, is 3125. But what about 5 to the 6th? That is what we want, isn't it? So we can now rewrite this as 5 to the 6th equals 5 to the y power. If the bases are the same, then we know y must equal what? 6. And so that tells me then that f of 125 equals now what? 6. I wanted to work that one